So, good afternoon and welcome back to the session for graph neural network. Um, we hadn't covered much in the first context session. I just gave you a brief idea about uh, the topics, a few of those topics, okay, as well as the whole course. These are the two topics which we have skipped in the last session. Okay, so we'll discuss the same over here, and then then we'll move forward. Okay. Now, before moving ahead, anything to be re-explained or explained, or any query to be resolved before we move ahead? I've uploaded the course handout. The EC1 dates are yet to be finalized. I have given it to the operation team. Operation team will confirm, will look into those dates, and once they confirm, then those dates will be disclosed to you. So webinars and EC1 dates. Anything to be covered before I officially start this session? No? Okay. But as and when the situation requires, I'll stop and I'll answer your queries. Okay, now the topic that we're going to cover, or that we're going to start away with, is the isomorphism in graph theory. So this problem is a very strange and very good, I'll say as a teacher, that is good to me, but the beauty or the good thing about the algorithm is it's this problem, the solution to this problem is very strange. Normally, till now, you might have heard that few of in any algorithm, either that belongs to the constant time algorithm, or linear, or square, or cube, or polynomial, or exponential, whatever it be. But this problem, isomorphism, doesn't belongs to the any category so far. Okay, so that means none of the mathematician is able to solve, is able to come up a fixed method that can reach out to this solution, that can reach out to the solution of to this problem. So there are certain steps that has to be followed, or that can be followed, but solution is not guaranteed that okay, you do 4 step, then you will solve half of the problem, or when you will able to solve, when you reach out to the 8 step, almost 90% of problem is solved, or something like this. So it's not so in this isomorphism. Okay, so this is the beauty behind the isomorphism, because we doesn't have this isomorphism doesn't belongs to any of the complexity classes. You have heard about the asymptotic notation. So there is no asymptotic notation that can be assigned to isomorphism problem. Neither big O of 1, nor big O of n, nor big O of n square, not n cube, not n to the power n. But the solution to this problem varies from linear time to exponential time. Okay. Before moving ahead, let me tell you what is the problem. What is the isomorphism problem is. You are given with a graph. Okay. So suppose this is one graph, and let me give you an easy example first. Okay, so suppose one of the easiest example that we always use is to explain the isomorphism is something like this. We have one graph. We have another graph. This is ABCD, a simple rectangle. Now C and D are twisted. Okay, so when C and D are twisted, it gives rise to the second graph. So this is G1, this is G2. The naming, I've used the same flow ABCD, but G1 and G2 are the same graph with a different orientation. Even this one also. So if this is a rectangle, okay, so either a horizontal rectangle or a rectangle or a vertical rectangle, it means the same. Okay, so earlier the rectangle was tending. Now it is in the vertical state. Now it is in horizontal state. This is also a same graph with a different orientation. So it's not necessary that you have to change the direction. You can just change the orientation also. The graph will be different. Now,
Sir, in
if I want to say,
sir, in G1 and G2, it should be C and D twisted, no? Means A and
but
D is connected,
I still
but
have
here A and D is not connected.
no issue. But I have this. This is just the name to those nodes. Okay, I'll answer the query. So we know that this is a same graph, but with a different orientation. It can be a different. We can say the twisting of those edges. Okay, or it can be different orientation of a graph. So here it is in a vertical state, it is in a horizontal state, but we know that this is the same graph. G1, G2, and G3, they all are same. Sorry, not C3, it's G3. They all are same graph. But until unless I have a proof, just by visualization, I cannot say, okay, for me as a human, it looks easy. I know that I have drawn the graph, so they are same. But in computer or in a program, it will be a matrix, I and J, where we have zeros and ones. Okay, so this may have a different zeros, combinations of zeros and one. G2 may have a different zeros and combination of zeros and one. G3 may have a different combination of zeros and ones. Means they may have different orientation, and we'll have to answer the query of either the same graph or not, just by going through those adjacency metrics. So for them, it is slightly different. G. Yeah, Vinash.
Sir, in G2 graph, A and C had one edge, but in original graph G1, there is no edge.
Okay, no issue. I have done it intentionally.
But then graphs will be different.
Okay. So that means G1 and G2 are different graph. That's what I want to say. They are different graph, but they are the different orientation of a same graph.
When we say orientation means possibilities?
No, orientation means the sequence of those nodes and the arrangement of those nodes and edges. So orientation doesn't have nothing to do with the possibility. Okay, orientation means the sequence of nodes and edges.
Got it.
The arrangement. The other word that I can use is the arrangement. Clear?
Yes, sir. Got it.
So let me, in any more query? Yeah, Shyam?
नहीं क्लास है तब तक से मिली लोग भी आ जाएगी.
Okay, Shyam, I think I request you to mute yourself. Shyam, any query?
No, sir. Sorry.
Okay, no issue. There's nothing like feeling sorry. Okay. Now, if I want to say that G1 equals to G2 or G3 based on those adjacency metrics, it's not that easy for me. As a human, just by looking at the graph, I can say, but as a computer or as a program, I cannot draw the graph on a paper. Okay, I'll have to execute the algorithm based on those adjacency metrics which have been in which the graph have been stored. So for that, I need to come up with a mapping that this A, this is equivalent to this one, this is equivalent to this one, this is equivalent to this node is equivalent to this edge is equivalent to this edge, and so on. So I'll have to come up with a one-to-one mapping of those nodes, by which I can say, okay, the node A of graph G1 is equivalent to the node A of graph G2. Node C of graph G1 is equivalent to the node D of the graph G2. Okay. So it may be possibility that the graph may be this. Okay. So A and C are connected. Okay. So in that case, now the C of G1 is equivalent to D of G2. So this, unless I have that mapping, I cannot say the graph as isomorphic. Okay. So ultimately, what is a graph isomorphism problem? Graph isomorphism problem is that you are given with two or more graphs. Somehow you'll have to come up with a yes or no answer that is this the same graph or a different. So that problem we call it as graph isomorphism, yeah, graph isomorphic problem. Clear? Any doubt regarding the definition of this problem? How we'll say yes or no, that is a different story. But somehow, in any way, if we can come up with that yes or no, whether two graphs are same or not. They may be different orientation, but the graph should be same. Clear? So for example, if we are given with those three set of graphs, same as the case the previous one, but this example is a bit complex. Okay, so there may be two embedded triangles. So in this, the orientation, or just by looking at the graph, I can say, okay, these are the two orientations, two triangles embedded, one embedded in the another one. Okay, but B is something different. The look of B is something different, and look of C is also something different. Just by looking, okay, I can say that, okay, B and C looks almost same, but I think they are different from A. But if we can come up with some method, we have a method, and we can say that, okay, so that means A and B are also isomorphic, as well as A and C are also isomorphic. That means all the three graphs are same with a different orientation. Here, the A of this graph is equivalent to A of node A of this graph. So B and this B is same as of this B. This C is same as of this C. This D is same as of this D. This E is same as of this E. And this F is same as of this F. So if we can come up with this one-to-one mapping, in which node of which graph is equivalent to which node of the another graph. So this relation is equivalent. Okay. Similarly, if I need to compare A and C, so node A of A is equivalent to node F of A. Somehow, by some way, I can come up that A to F, A is equivalent to F, B is equivalent to B, C is equivalent to A, D is equivalent to C, E is equivalent to E, and F is equivalent to D. If we can come up with this type of mapping, then I can say that, those two graphs are isomorphic to each other. Now the question arises how we can come up with this mapping. Okay, so this I'll explain, but as of now, is the problem clear? Now, why I'm investing much of the time in this problem is because this is a necessary evil, like a friction. This will be a part of each and every activity. Yeah, Arun, Acha. Okay, and any query to be resolved?
So by looking into the
how was A equal to C?
This I'll explain you. A was not equal to C, A was equals to equivalent to F. Okay, fine. Second question.
So by looking into the neighboring node, we can identify, right? So we are saying A equal to F, right? A has the same neighboring node as F has. So we can say A equal to F.
We cannot say that two graphs are isomorphic.
I mean, for all the nodes.
For all the nodes.
Yeah.
Even if we miss one, let's suppose, for example, a graph have 10 nodes, we are able to come up with the mapping of 8, and 2 are not mapping. Well, those two nodes are not equivalent. Then in that case, we'll say that those two graphs are not isomorphic. Then we come up with the idea of similarity. Those two graphs are 80% similar to each other. There's a 20% difference. So we'll take this isomorphism to the different problem of similarity or pattern matching, pattern identification. So that has to be structurally same. Now, the good thing or the bad thing is there is no fixed method, there's no fixed algorithm which says that if we follow those, we can come up with this mapping. So this is just a hit and trial method. You'll have to do a bit of changes, and somehow if we are able to get it, you can answer this query just by in a linear time, or it may takes up to the exponential time. Means you'll have to check for each and every possibility in order to say yes or no. Now, what is the steps for the isomorphism to check? So first of all, we'll check the number of nodes in a graph. So number of nodes in a graph should be same in both the graphs. Okay, so at the time it is a pairwise comparison. So we'll be doing 2 at a time. If we have to compare with three graphs, then we cannot do it all 3 at a once. We'll have to do pairwise. Okay, so this is a pairwise activity. So first thing that there are certain checks to be passed through. So first check is the graph, the number of nodes in both the graph should be same. So if number of nodes in both the graph varies, then we can say, okay, those two graphs are not isomorphic. Fine, we can terminate the algorithm. So it's easy to say no in this case, but to say yes, we'll have to check for each and every possibility. So the first step is the number of nodes in a graph. Fine. Then the second step is if it is passed through. Okay, so that means the number of nodes are same. Okay, so that means I'll say that, okay, number of nodes in both the graphs are same. So the two graphs can be or may be isomorphic. Then move to the next step. Next step says that, first of all, count the number of edges. So if the number of edges is also same, then I will move to the next saying that, okay, the number of edges are also same. Then those two graphs may be isomorphic. If number of edges are different, then straight away, no, the two graphs are not isomorphic. Fine. Then the third step is the number of nodes are same, number of edges are same. Then we check the degree of a graph. Degree of a graph means the node with the highest degree. So the degree of a node having the highest degree, that will be the degree of a graph. So even if the degree of a graph is also same, then we can say, okay, the degree of the graph is also same, though then in that case those two graphs may be isomorphic. Fine. Then move to the next step. Then we check for the orientation. That, okay, there are 3 nodes with degree 3, there are 2 nodes with degree 2, and there is 1 node with degree 1. Is it the same in the another graph? If there's an exact match, there are 3 nodes with degree 2, 2 nodes with degree 3, and 1 node with degree 1, then we can say, okay, the sequence of degree is also same. Fine. So in that case, those 2 graphs may be isomorphic. If there's a mismatch, we can say no. Then we check for the orientation. Okay, the node, that's again a hit and trial method. So a node having degree 3 is surrounded by a node with degree 2. Okay, so that means, so suppose, for example, if this is one case, and the another graph can be like this. Parallel nahi karte, because we are focusing only on the, let me draw 3 different graphs to make you explain. Okay, so that means, fine. Let me have a different orientation for this. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, there's a complete path. One, there's a complete path, and one has degree 3. One has a degree 3. Is it so? Okay. So number of nodes, 1, 2, 3, 4, 5, 6, 7. Number of edges, 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I'll have to draw one more edge. Is it so? Is it so now? Let me check. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, fine. So both the graph has 7 nodes. Fine, I cannot deny it. Both the graphs have 10 edges. I cannot deny it. What is the highest degree of a graph? So the degree of a graph is 3. Degree of a graph is 3. Here also the degree of graph is 3. Fine, I cannot say anything about the isomorphism. How many nodes are there? 1, 2, 3, 4 nodes are there with degree 3. 1, 2, 3. 1, 2. मुझे इसमें कुछ गड़बड़ लग रहा है. 1, 2, 3, 4. There are 4 nodes with degree 3. दोनों ग्राफ सेम नहीं है. 1, 2, 3, 4, 5, 6. यहाँ 6 nodes है with degree 3. हाँ. So in that case, चलो अगर बन ही गया गलत एग्जाम्पल तो गलत ही प्रूव करते हैं. Now here 1, 2, 3. There were 4 nodes with degree 3, and there was 1, 2, 3 nodes with degree 2. Here there are there's only one node with degree 2, whereas 1, 2, 3, 4, 5, 6 nodes with degree 3. So that means there is the orientation is not same. So we can say that it is not isomorphic. So it's easy for me to say that, okay, fine. Wherever there's a mismatch, I can say, okay, there's a mismatch, those 2 graphs are not isomorphic. So suppose now, if, just give me a minute. There was some unregistered student in the class. Okay. Now, so suppose here also, so there is an, this is okay, fine. Luckily, we have come up with an example where at the third point we came to know that those two graphs are not isomorphic because the degree sequence doesn't match. Okay. So that means if I make some changes into the current graph and somehow if I still make it isomorphic, then these are the two examples. Okay, so that means the orientation is also same. K means a node with degree 3 is, so there are a node with degree 3 here. Two nodes with degree 3 is surrounded by a node with degree 2. Is it so? No, this is not the case because all the nodes with degree 3 were in neighborhood to each other. They were direct neighbors. Okay, and there was only two neighbors of nodes with degree 3 having degree 2. This one and this one was those two nodes in the neighborhood of nodes with degree 3 having a degree 2. Whereas this is not so because there's only one node. There is a there are three nodes. One in the neighborhood of this, one in the neighborhood of this. Matlab, a node, although there are two nodes with degree 2 surrounded by nodes with degree 3, but there was no node, there was one node in G2 which was surrounded by a node with degree 3, both the points, both the ends, which is not so in this case. Okay, so a node with degree 2 were having a node with degree 2 on one end definitely. Both the neighbors of node of degree 2 were not surrounded by a node with degree 3. So somehow if we can come up with this logic, this idea, this pattern, we can say that the graph was not isomorphic. But if we are working on those two graphs, now all the nodes are of degree 3, all the nodes are of degree 3, fine. So there is no change of orientation. So or if the degree sequence we cannot check because all of them are degree 3. Okay, then we have to come up if this is the last hit and trial method. Okay, so if that orientation is also same, then also I cannot say that both the graph are isomorphic. Okay, in order to say that both the graph are isomorphic, I'll have to come up with the mapping. Unless I come up with this one-to-one mapping, I cannot say anything about the isomorphism. So if we come up with this mapping, then I can say, okay, I have found one mapping, at least one also. If I found one mapping, one-to-one mapping, so that means those two graphs are isomorphic to each other. Okay, now it's easy for us as a human to say, okay, just this is twisted or this is what. Okay, if we change an orientation or something, but for a computer, how that sequence or that one-to-one mapping can be identified. One way is you have an adjacency matrix of G1, you have an adjacency matrix of G2, you perform row and column transformations. Okay, so you make changes like a we can say Rubik cube. So you perform the row and column transformations such that after doing a number of row and column transformation, you convert one matrix into another. Okay, so the moment you have converted one matrix into another, that sequence of nodes which are there in the indexes will be the mapping of those two graphs. So suppose how to do that. So suppose, for example, somehow we have performed those row and column transformations. So this is for G1. So G1 is A, B, C, D, E, F, G. Okay, the same A, B, C, D, E, F. Now, if I have come up with the mapping, the sequence would have been F first, then B, then A, then C, then E, then D. So now those two matrices are almost same. This mapping, this sequence of nodes will be my mapping, one-to-one mapping. If I am able to do so, I'll say that those two graphs are isomorphic to each other. Okay, so it may be possible that you perform 2 or 3 rotation, you came up with the mapping, or you'll have to check for each and every possibility, means n cross n. The complexity varies from big O of n to big O of n cross n. If you're lucky enough, you make some changes, okay, and you may get, okay, that is the same mapping. So that means we are done. So it may be in the first few attempts, or you will have to check for each and every possibility in order to say yes or no. No is easy. The moment we find a mismatch, we can say, okay, no. But if we have to say yes, we'll have to check for each and every possibility. Even there may be a chance that n cross nth iteration might lead to the isomorphism. Okay. And if it also doesn't match, then we can say that, okay, so no is also towards the n cross n. Okay, but yes can only be confirmed if we are able to come up with the mapping in between, or we'll have to check for each and every possibility. And there is no specific deterministic way of doing it. So that will be a problem for us. Okay, now this isomorphism will be used to answer the query regarding the similarity. So if you're given with two graphs, I say that, okay, how similar those two graphs are. So if I'll have to answer, or if I'll have to identify the 100% similar graph, 100% same pattern with a different orientation, then again that's a problem of isomorphism. Okay, if I have to find out the similarity, 100% similar map, then again that's a problem of isomorphism. Its relaxed version is similarity. Suppose 50% similar, 70% similar, and so on. Okay, fine, good. Is this problem clear? Why it is, how it is, and what about, okay, there was a query. Why does the node and vertex mapping not important in isomorphism, but relationship edges are important? My understanding is isomorphism will not be unique. If we all do it, everyone will have their own perception. Will this isomorphism being not unique lead to a different answer? Sorry, I'm not able to get it. I'll read it again. Why does the node vertex mapping not important in isomorphism? I think the final answer can be done. Final statement can be made about the isomorphism only if we are come up with the node one-to-one mapping. Okay, so I think this statement is not correct. Vertex mapping. Okay, if you're talking about that the sequence. Okay, so you'll have to come up with the sequence. But relationship edges are important. I think both are important, and node one-to-one mapping is the final phase of saying yes. My understanding is, okay, fine. Let me see what you have understood. Isomorphism will not be unique if we all do it. No, there may be a different orientation. Okay, but our algorithm should be in a position to answer yes in all the cases. So for example, in this B and C, A, B, and C are three graph. I'm not saying that, okay, I'll have to compare A with C. It may be possible that I'm given with this C graph, and I'll have to compare it with A. So then that mapping has to be from C to A, not A to C. Okay, so it should be unique. Matlab, that one-to-one mapping has to be there. Until unless we come up with that one-to-one mapping, we cannot say anything about the isomorphism. So will not have a unique. It will be a matlab, it will not be that unique. If we are comparing this with this graph, then mapping will be this. If I am comparing with A and C, the mapping will be this. But for A and C, the mapping will be Acha, in that sense, in sometimes if they can be unique, they cannot be unique if it's like this one. Suppose it's like this. Okay, all the nodes are of degree 2. Then A, B, C, D, then A can be equivalent to B, A is equivalent to C, A is equivalent to D also. In that sense, it is not unique. Not always. The special case is this. But we'll have to come up with a mapping. But will have their own perception, but it is not based on the perception, it is based on the scenario. If the degree is same for all.
Yeah, the idea is there can be n types of, like we did in the first case only. We had one mapping, and then we have A to B and A to C. If we go with a question like a GNN problem, will the outcome be different if we take any of the cases?
Our answer is yes or no. Whatever the mapping is, if we're able to come up with the mapping, what type of mapping it is, I'll say, okay, this graph is isomorphic to this one. So A and C, A and B are isomorphic, A and C are isomorphic. It may be possible that you may come up with same, suppose for example, this D and this F. It may be possible. It may be one other mapping. So A is equivalent to D and D is equivalent to F. It may be possible, but even if we are able to get up at least one mapping, our work is done. We need not to check for each and every mapping. How many possible mapping can be there? Clear?
Then I understood. Like algo would be able to understand. Then that should be a requirement then.
At least in any of the mapping, but at least one-to-one mapping.
Got it.
But answer will be there will not be different answers. Either it will be isomorphic or not. The answer may be different if we have to identify, okay, if not exactly similar, then to what extent they are similar to each other. Two graphs. Okay. Is it okay? Should I move forward? Okay, fine. But there is one sub problem which I say subgraph isomorphism. When you will Google it about the subgraph isomorphism, this problem is proven to be NP complete, NPC problem. Okay, I'll explain you what this NPC means. Is it there in my it is there in these slides. Okay, so if this NPC is confusing you, as of now you can skip. As of now you can say difficult to solve problem. Okay, fine. Now the second concept that I'm going to explain is the bipartite partition. That will be useful when you or multipartite graph. Okay, this concept will be useful when you are dealing with the knowledge graphs. Okay, or heterogeneous graphs. I'll speak the definition. I'll read out the definition first. Not read out. I'll say the definition first, and then I'll explain. A graph. Sorry, not two. A graph is said to be bipartite. Bi means two. Partite means partition. Okay, so that means a graph has to be, or means that node of those graphs have to be divided into two different set. Okay, so that we call it as bipartite. Mother two partition. So a graph is said to be bipartite if all the nodes of the graph can be divided into two different set, okay, such that both the sets are mutually exclusive and collectively exhaustive. Now, mutually exclusive means two partition. So if all the nodes, so suppose for example, if it is A, B, C, D, E, so a node A should belongs to only one set. So every node should belong to only one set. Okay, so there is no overlap. A node should not belongs to more than one partition. So that type of set is called as mutually exclusive. Okay, and collectively exhaustive means all the nodes of a graph should be a part of one or the other partition. So it should not be the case that A, B, C, D, E, F, F is not a part of any partition. No. If there is a node in the graph, it has to be either in a partition 1 or partition 2. He cannot roam around here and there alone, or he cannot have his own choice. He'll have to be a part of either partition 1 or partition 2 if it is bipartite. If it is multi-partition, then it has to be a part of any partition. He cannot be a isolated vertex, or we can say roaming around. Okay, free vertex. It cannot be a free vertex. So I'll repeat the definition again. A graph is said to be bipartite if the graph can, the nodes of the graph can be divided into two partitions such that the set is mutually exclusive and collectively exhaustive. And there's one more condition. The condition is, and if there is an edge, so if there is an edge in a graph, it has to be from one set to another set. Okay, so that means what is the hidden definition behind this? The hidden definition behind this is key. The nodes of the same set cannot be connected together. Neither this nor this. If there is an edge, it has to be from one set to another set. It cannot be between the nodes of the same set. So if this condition satisfied, then that graph will be called as bipartite partitions. Clear? Fine. One example. Suppose I have a graph in which the nodes are the diseases two type of nodes, okay, diseases along with the medicines or salt. So a particular disease is caused, either it can be a causing graph or it can be a curing graph. So it may be possible that certain kind of element is responsible for certain kind of cancer. So if that cancer is in that chemical is into your body, it may arise to that kind of cancer. Or so it can be a edge of causing, it can be a edge of curing as well. So a certain kind of salt is used to cure a certain kind of disease. Okay, so this can be the element and the disease. Okay, so this can be an example for a knowledge graph where a nodes, there can be multiple type of nodes. So somehow, so if one disease cannot be responsible for another disease, one salt cannot be used to cure or we can say cause for the another salt. Okay, so that somehow that relation exists, although we had example, but okay. So that is the case where there cannot be an edge between these nodes of the same set. If it has to be, it will be from disease to salt, either for causing or for curing. So clear with this bipartite graph and its real world application? Like a recommendation system. So a particular set of users to be recommended by a certain kind of offers. So who should get what kind of offer? So as a part of recommendation system also is an example for bipartite partition or multipartite. Clear? Clear with this? At least say yes. Am I audible? Okay, fine. Fine. Now I think you might have heard a lot about NPC. I think this was the last module of your DSAD course. Any idea about NPC? What does NPC means? And what is the basic interpretation of each word? You can Google it up. It will give you answer. NPC, most of the time, we just wrongly say that non-polynomial computation. Okay, so it's not. NPC is something. It is non-deterministic polynomial. Non-deterministic polynomial. So that we call it as NP. And C is complete. Okay, so as of now, I have to explain it. Do you have any, if you do have a complete idea of NPC, then I think I need not to invest around 10 to 15 minutes on this. I can skip it and I can move to the next one. If you have an idea about non-deterministic polynomial, what exactly does it mean? And what is deterministism? What is determinism? Why it should not be polynomial or something? No, this no is means. Achha, no idea. Okay, no issue. I'll explain. Okay, this again will be a story. You'll have to be with me. Okay, all the algorithms in your DSAD course or in your any of the machine learning and all, if you have learned all the algorithm that you have covered, shortest path and all, minimum spanning tree, shorting algorithm, searching algorithm, binary search tree, KD tree, double-ended queue, many. All the algorithm was deterministic algorithm. What does a deterministic algorithm means? A fixed set of steps, are written. So you are given with an algorithm. That algorithm is being developed by a bunch of learned person, and that is complete, not complete in the sense that is perfect. Okay, and if you follow those steps, definitely it is guaranteed that you will reach to the answer, that you will reach the solution. So those type of problems are called as deterministic problems, where each and every step is fixed, and it is guaranteed that if you follow those steps correctly without making any mistake, definitely you will reach to a solution. So those type of problem are called as deterministic problem. Fine. Now what all are the non-deterministic problem? So non-deterministic problems are the problems in which you have some fixed set of steps, but either some decisions have to be made randomly, or some probabilistic decisions need to be made. Means some decision has to be made based on the probability. So those set of steps, those set of algorithms are called as non-deterministic algorithm. The best example that you have learned is your random quick shot, in which selection of pivot was done randomly. So all the random algorithms in which in anything you are deciding in your ACI course, artificial intelligence course, all the hill climbing approach, genetic algorithm, and particle sum optimization, and all those things in which in genetic algorithm you were choosing which crossover to be used, what should be the mutation percentage, what should be the crossover percentage in an unclean optimization. You just come up the values between the local best and the global best. Okay, in particle swarm optimization. In uncolony optimization, that local pheromone and all those local min and global min max. Okay, so the variation between those two, exploration and exploitation, was done randomly. Was done probabilistically. So the crossover probability was fixed at 70%. So that means you generate a random number. So if in any probability is 70%, I think I have explained you 0 to 1. If I say probability is 70%, means 0.7, I fix up a mark. Then I generate a random number. If that random number is between 0 to 7, I'll say yes. If that random number generated is from 0.7 to 0.1, I will say no. So this is how random the probabilistic activities are being done into the algorithm. Okay, I think in your ACI course, in your deep learning course, you might have worked on the random walk. Okay, random walk means to move ahead or not. We'll be using the same over here also. So random walk means we randomly choose which algorithm, which path to trace forward. But somehow, so all the algorithms where either we have some probabilistic activity or some random activity is being conducted or computed, then those set of algorithms are called as non-deterministic. So all the randomized algorithms comes under the set of non-deterministic algorithm, as well as the probabilistic stochastic algorithm. All the stochastic algorithms which works based on the probability, they all belongs to that also belongs to the category of non-deterministic algorithm. Means they are not deterministic, they are random, either they are probabilistic. Okay, so got the difference between deterministic algorithm and non-deterministic algorithm. Non-deterministic comprises of random algorithm and stochastic algorithm. Stochastic algorithm can also be called as the probabilistic algorithms. Okay, clear with this non-deterministic, deterministic and non-deterministic algorithms? You'll have to say yes to me. If not, I'll explain it again. Okay, fine. Now, so this is the difference between deterministic and non-deterministic. Now, the second story is regarding the complexity. Let me change the color. All the asymptotic notations that you have learned so far varies from big O of 1 to big O of n cross n, or e to the power n, or 2 to the power n, or something. Okay, means constant to exponential. Okay, and if any algorithm has exponential time complexity, what does it means? Same like isomorphism. Okay, you'll have to check each and every possibility in the worst case to get the solution. So this is the last known upper bound for the complexity of any algorithm, exponential. Okay, so constant plus something ahead of exponential means n square, big O of n square, n cube, and in that flavor n to the power 4 also. Okay, belongs to the category of x, belongs to the category of polynomial. Okay, beyond that it is exponential. Exponential means exhaustive. Okay, so polynomial means, or usually most of the time it is still n cube. Even n to the power 4 is not acceptable. till n cube, or we can say, chalo, theek hai, as of now, just for sake of simplicity, I can say n to the power 4 also is acceptable. I can put it into the subset of polynomial time algorithm. Okay. Even the shortest path and all, I think you have learned or you have heard that it was n cube to the n to the power 4, somewhere between n cube and n to the power 4. So those complexity will be called as polynomial complexity, means n square, n cube, n to the power 4. Okay. Now again, a big story. Not big story, again a storytelling. So non-deterministic polynomial. So now NP, so all the algorithms which from 0 to this set will be called as P set, mean polynomial time algorithm. No, I should not say P set, because P set might lead to a confusion to P space problems. Polynomial time. Why polynomial time algorithm? Because they are comparatively doable. Okay, when it requires lesser amount of time and durable and doable. So a problem is said to be polynomial if it can be solved in O(n) square, O(n) cube, or n to the power 4 times. Okay, fine. Now NP, non-deterministic polynomial. So if a problem is said to be, or time complexity of a problem is said to be NP, non-deterministic polynomial, what does it mean? That if I want to solve the problem deterministically, then it requires exponential time. But if I want to solve it in a polynomial time, I'll have to solve it in a non-deterministically way. So deterministically, I hope I have not confused you. Deterministically exponential, but want to solve in polynomial time, then I'll have to use non-deterministic method. Means stochastically I can solve a problem, or randomly I can solve a problem in a polynomial time. But if I want to go for a deterministic method, then definitely I will be able to solve it in a polynomial time. So those type of problem are called as NP, non-deterministic polynomial. Okay. So NPC means non-deterministically polynomial space polynomial time problem, NPC problem. P space is something different, which is unsolvable or solution not known. So if there is anybody, so in P space in NP complete, so that is NP, non-deterministic polynomial. NPC means if someone knows the solution to a problem. So deterministically, if I want to know, or someone knows the solution to a problem, then definitely it is exponential. Okay, so is this NPC complete? Sorry, NPC problem. The definition is clear, concept is clear. P space is one step ahead. So if I draw a diagram, so polynomial time means constant time. Okay, big O of 1 is one set. Then above it is polynomial. Then above it is NP, non-deterministically polynomial. Then NPC problem. Sometimes NP and NPC can be overlap. And then we have a P space. P space means nobody knows what is the exact, either the solution is not known to you, okay, or it is known to be exponential. So that's unsolvable, yeah, unknown solution problems are called as P space.
So what is
Clear?
here complete? I mean, we have NP complete and NP hard also, right?
NP hard is one step ahead of NP complete. So if okay, NPC and NP hard is one step ahead, one step above the NPC problem. So NPC are still solvable, doable. Okay, NP hard means difficult to solve problems. And most of the PhD topics are from the area of NPC and NP hard.
So NP hard means we don't have solution, but we can verify whether it is solvable or not.
Difficult to solve problems.
Okay.
Difficulty is in NP hard means difficult to solve problem. The problems whose solution is difficult, either not known to us, or if it is known to us, then also it is exponential. So sometimes NPC and NP hard can be overlap also. Yeah.
नहीं जा रहा
Complete stands for no, this I didn't have an answer for Shakib on this. What does complete stand for? I need to think of. Okay, break. Okay, we'll have a break for around 3 minutes. Is it okay? In the meantime, I'll search for this NP complete. This complete stand for. Okay, so is it? Do you need a break for longer time, or 2-3 minutes are okay?
Okay, 2-3 minutes are okay.
Okay, so at 2:46. Make it this one. 3 minutes is fine. Okay, so we'll start again at 2:46. We are getting a resound when someone speaks. This is a problem in the Teams this semester. If I'm speaking, there will not be any echo, but if someone else will be speaking, even when my mic or speaker is on, I need to check. Okay, so there will be an echo. So if someone is raising any query, then rest of all will hear an echo. No, I'm using the laptop only. So I think that this may be problem with my laptop then. The other faculty uses headphone. To speak, Anirudh? Laptop sound, speaker sound is captured by an echo. We attached CV class. It was smooth there. He hadn't used headphone there. But I'm also, there's no device connected to me to the laptop. Simply, I'm using the speaker. Okay, so in that case, that problem may be with me only. So after this, I'll talk to my team. Okay, what is the problem? It may be possible, or but in that case, if I'm speaking and I'm listening to you, then both my mic and my speaker has to be on. Even if I turn off the speaker, then I'll not be able to hear what you're speaking. And if I turn off the mic, then you won't be able to listen what I'm speaking. But is it not so when I'm If it is, then it should be there continuously even when I'm teaching you. I'll use the headphone. Okay, fine. Many more concepts to be covered. Will I be able to finish it today? I'll try to finish it. Okay, should I continue? Okay. So graph matching, okay, or edit distance. So this may be the one relaxed version of the graph isomorphism. Now, matching means to what extent the two graphs matches to each other. Okay, if it is 100% matching, then graph isomorphic problem. Its relaxed version is the graph similarity. To what extent those two graph match, or to what extent those two graphs are similar to each other. Okay. But there's one word which we will be using very frequently. It is called as edit distance. What does an edit distance means? It is a relaxed, so it is used in a relaxed version of graph isomorphism problem. Means we are given with a graph G1 and a graph G2. We know that they may be same, they may be different. And most of the time, as of now, we convert them as a we consider them as a different one. But somehow we are allowed to make changes in G1 such that after certain changes, the graph G1 is converted into G2. Okay. Now, what all are the operations that are allowed? So, for example, I'm allowed to add a new edge. Sorry, I'm allowed to add a new node. I'm allowed to merge two existing node. I'm allowed to delete an existing node. I'm allowed to add a new edge into the graph. I'm allowed to merge two edges in a graph. I'm allowed to change the orientation, swap the two nodes or two nodes of a graph. Okay, so that means I'm allowed to do certain changes into a graph. But what is my motto? My objective is that I wish to convert one graph into another. So the number of operations done while converting one graph into another will be equivalent to the edit distance of the graph. Okay, so I repeat the definition again. The edit distance of a graph is the number of operations allowed or number of operations performed on a graph such that one graph is converted into, the given graph is converted into the another graph. The operation allowed are, we are allowed to add a edge, we are allowed to add a node, we are allowed to delete a node, we are allowed to delete an edge, we are allowed to merge a node, we are allowed to split a node, we are allowed to split an edge, we are allowed to split a merge to edge. Okay, so all these operations are allowed, but our main motto is we'll have to convert one graph into another. So that means initially one graph was not equivalent, was not isomorphic to another. They were non-isomorphic, but somehow we are converting one graph into another by either shrinking it or by growing it. So the number of operation done will be called as the edit distance of a graph. So for example, if this is our one graph and this is our another graph, okay, so that means if we add two edges, G1 will be converted into G2. So the edit distance of a graph will be 2, in which I have just added two edges. Clear? Subgraph isomorphism I have already explained. This is proven to be an NP complete problem. NPC problem. Proven. Okay, now, again a question. How can you prove that a graph, that a particular problem is proven to be NP complete? If I think you have learned in your DSAD course, the last topic was, okay, let me finish that. The last topic was the 3 satisfiability problem. Set. Okay, and its subset was 3 satisfiability. A special case was 3 satisfiability problem. So if somehow you can reduce and 3 satisfiability problem is proven, or satisfiability problem is proven to be an NP complete problem. Okay, so if somehow you can reduce our problem into 3 satisfiability problem, then that problem will also be NP complete problem. So that is subgraph isomorphism. Okay, let me answer the query. A problem is NP complete if it is NP or NP hard and NP hard. Okay, NP hard might not have a solution, but can be verified in a polynomial time. We can say that. Okay, splitting of an edge. Splitting of an edge, I should not use the word. What is a splitting of an edge means? Splitting of node is okay. Splitting of an edge can be possible. So if this is an edge E1, it split and make a parallel edge. It can be an intermediate. So a parallel edge is created. Clear? Okay, summarization. Again, I think graph summarization means whenever we are given with a bigger graph, we'll have to extract out, or we store or perform the operation only on the important part of a graph. So that we call it as graph summarization. Means like the we can say the example can be the image.google, no, not image, maps.google. Okay, so suppose, for example, if this is a perfect example for graph summarization and all. So suppose if I'm at a particular point, so right from the area of Muradabad to Shadilpur, after Pakistan or within the Pakistan? Pilani, it is in the Rajasthan. So right from the Dehradun or Uttarakhand and Pilani and Rajasthan, I'm able to see. Okay, so the important, or we can say, not all the cities are visible to me. Only some big cities which have the population or the size beyond a threshold is visible to me. Okay, so Delhi, Faridabad, and Aligarh, Agra will be somewhere there, and so on, Palwal and all. But if I zoom out, and first of all, if I zoom out, even that information, a new information will be visible, and some information which was earlier visible, now it is not visible to me. So suppose, for example, this Gajrala was visible to me at this point. When I zoom out, it disappears, because now at this point, it is not that important. Even when I zoom out more, some more cities got disappear. So that means at this scale, those cities were not visible. Now, when I zoom in, some new areas which may be important in the scale are now visible. So even in Noida, not much of the information is visible, simply few. Even in Gurgaon, no sectors, nothing is visible to me. Now when I zoom in more, now something else is visible. Okay, and so on. So this is an example for graph summarization. What summary should be visible to me at what time? That would still be the same as, right? How would it be called as a split without an intermediate node? Going deep, I've not even thought of splitting of edge. I need to rethink whether I should include that splitting of edge or not. I need to rethink. To be very frank, I have not even thought of, okay, what does a splitting of edge actually means? In the flow, I have I've spoken that word, and I've tried to justify it by creating a parallel edge. But what exactly does the splitting of edge means? I need to rethink it. Okay, so I'll make a note and I'll answer your query at the end. Okay, when off the record or towards the end also. And as of now, I think splitting of edge can be dropped from the sentence of edit distance, from the definition of edit distance. Okay, adding of splitting of node can be justified, can be explained, but splitting of edge, I need to check whether is it there officially or not. No, in that case, that will be the introduction. If I introduce an introductory node, that will be an introduction to a new node, intermediate, and that can be split. Okay, in some sense it can be. Merging of edge, merging of edge I can explain. Merging is proven to be complete. Proven is a part of that definition. So if there is two nodes, suppose for example 3 nodes connected to each other, a 4 node connected to each other in that way, and if I assume if I merge those 2 nodes, then my resultant graph will be, this is something different. These 2 nodes is now merged into one. This edge is still, now this was from A, B, C, D. So this is A, this is D, and this is BC. Okay, so earlier D and C was an edge and D and B was an edge. Now D, there will be a parallel edge from D to BC. One is this, one is this. Now A to C, there was a separate edge. A to B, there was a separate edge. Now there'll be 2 parallel edges to BC. A to B and A. So A to B will now be A to BC, and A to C will again be A to BC. So this how the merging of edge and this edge will become a self loop. Clear? Okay, so summarization, sampling. Again, sampling means just like an ISM. Okay, if the whole bunch of population is not accessible or available to us, then we can extract out the sample. such that that sample is an actual representation of the population. Same is the case over here. Graph sample means some experiment or some study cannot be done on an actual graph. Either the graph is not accessible or it is not feasible. So in that case, we will be doing the experimentation on the sample of a graph, on a subset of a graph, which works as a which behaves as a complete graph, and that we call it as graph sampling. Partitioning again, in an we can say generalized version of graph bipart. Bipartite is a special case of partitions. So partition of a graph means dividing the graph into a different set, such that they have each set specify a common property. So that we call it as graph partition. Now, simple in a graph partition, the partitions can overlap. Okay, so partition can overlap, and the criteria for creating a partition is user defined. Usually, if that partition is clustering, then it is based on the connectivity. The connectivity within the partition has to be dense, and across the partition can be sparse. If it is based on the communities, if it is based on the attributes, then all the nodes that belongs to the same set should satisfy some property. So that we call it as community detection. Sometimes community detection and graph clustering can be different. Sometimes they can be the same. Okay, but clustering definitely is based on the connectivity, and community is based on the attributes, based on the properties. Okay, if that property is connectivity, then clustering and community is both the same. Okay, so cut vertex means, I think I've already explained you cut vertex and cut edge, or you also know about it. So a set to be a cut vertex, if we remove the graph, that vertex from the graph will become disconnected. It can be a single vertex, it can be a set. So cut set means a set of vertices will be called as cut set if we remove them from the graph. Means if I'm removing a node, then all the edges associated with that node will also be removed. That's an obvious thing. So if those set of nodes are removed from the graph become disconnected. So that set of vertices are called as cut set. Okay, if this and those vertex will be called as cut vertex. Yeah, cut vertices if they are multiple. Then same cut edge, we can say edge set also. So means removal of that edge makes the graph disconnected. So it can be a simple edge, it can be a single edge, it can be a collection of edges also. So if certain number of edges are removed from the graph, multiple bridges can be broken, can be demolished, that cuts one city from the rest of the country. So those bridges will be the candidate of the edge set, cut edge set. Okay, bipartite graph I've already explained. Clear? U and V can be splitted. U to W, W to V, map. Okay, example, while zoom in, you can have one or more cities introduced between two cities. In that sense, splitting of edge can be possible, okay, by introducing a new node in between the path. Okay, like your we can say running time information of a train. Okay, runtime information in which the stations where the train is not halting are hidden. So 12 intermediate stations between two halting point. So in that case, we can click and get those stations, but those stations are not important for me because in that graph, because those are not the halting stations. So in that sense, we can have the splitting of edge. Okay, but split. But in this example, so Bhupen, thank you. But if that splitting of edge will be a candidate of addition of new vertex in the graph. So in this case, splitting of edge UV and introducing a new node W in between U and V, the both will be same. So in that case, yes. So thank you, Bhupendra. Okay, now any more queries? Chalo. Now walk. This will be this word we will be using in this course very frequently. This is the another word which we use, random walk or random restart. So if I'm given with a graph, not specifically, chalo, theek hai, let me draw a dense graph in between. Chalo. So this may be a dense graph. If I'm working on a random walk, then I should identify a starting point. Some S has to be identified, or this S either should be given by the user, or this S can be chosen randomly. Okay, so a walk is said to be random if there's any user that start from any node of a graph, moves across the edges in a graph randomly. So which edge to be used is decided randomly. So it's not necessary that he should move ahead. He can come back to the original path or the original or already visited node as well. And then he can move to the new path. So the path can overlap. But which node to be visited or which edge to be traversed is purely decides at random. So that type of movement, that type of path is called as random walk. Okay. Now, what is the physical interpretation of this? So for example, in the Instagram, Facebook, even now in YouTube's, wherever you have those shorts and reels. Okay. So, and even in the Google surfing as well. So you start with a particular video and then you scroll up, some you skip, and then you watch a certain video. You may like it or not. Certain times, okay, suppose you watch it to the beginning, initial few seconds, and then you scroll up again. So that's again that can be considered as a walk. Okay, you started with a particular type of video, then you move across the graph, you halt on a particular video, you watched it completely. So that means the type of video that you're watching to the complete will be added into your own viewing history. And that will be used as a for the recommendation algorithm. Then if you have watched one kind of video, similarly in the next, because the graph, that list is randomly generated and randomly updated. The moment you have watched a particular type of video complete, the next or a few more videos will be of similar type. Okay, so that type of movement is used in a recommendation system very well. Random walk. So that the recommendation engine is learning starting from the about your own views, type of views, or what next to be suggested based on the type of video that you are that you have viewed in the past. Okay. Similarly, that can be used for the sequence also. So when you're typing something, typing a letter or on a WhatsApp, text, we can say text prediction. Okay, word prediction. So if you're typing a particular word into a WhatsApp, okay. So suppose, for example, I'll show you. Usually, when I wish anyone, what the normal sentence that I used to use is, wish you a very happy birthday, dear sir or dear madam. Okay. So this is my format that I have been using every time. If I am wishing anyone congratulations or birthday, then I think this they will not be suggesting. I think in the phone, I can show you, but I think I cannot show you my phone at this moment because that's not with you. That's not with me. But in my phone, when I type wish, you automatically appears along with few more suggestions. The moment I wish you the moment I type very, then rest a very happy birthday, dear sir or dear madam, they appears in the suggestion. Okay. So that again can be type of a random walk based on the recommendation. So we can say that we have a word VAB, okay, and which path I have been following very frequently. So the moment I have stepped into that path, the whole paragraph can be instantly suggested to me. If I say wish you a, that means very happy birthday, dear sir or dear tak, it automatically suggested and it can be, I can select and I can go. Even the Google Mail is also using some kind of this. So the type of text that you are typing frequently. Okay. So that means suppose for example, dear sir or dear something. Okay. Now, if it have been, the mail have been sent to you by someone else, for example, this is something related to, I'm not sending it to you. Okay. But is it not working? But when I say type dear sir or Suresh, okay, for Suresh, I rarely use, I rarely used to send those mails through the name. So that's why he had ignored Suresh word. For Suresh, I have also always used sir. So this have been suggested to me, something like this. Okay, so this can be a one example for the recommendation system. So random walk is the first method to make or to generate an initial sequence for anything. And in the graph, it will be a path. It will be a sequence of nodes traversing through some edges. So that we call it as random walk. Click is almost complete graph. Okay, so this is the relaxed version of complete graph. What is a complete graph? A graph is said to be complete if every node of a graph is connected to every other node of a graph. So that is complete graph. Its relaxed version is click. Almost complete means very dense graph. But not complete, almost complete graph. So those are called as clicks. So pattern matching, again, frequent pattern matching. So pattern matching means again the problem of isomorphism will comes into play. I'll have to identify what pattern have been repeated frequently. So pattern means pattern and its orientation. Repeated frequently throughout the graph. will be a output on a pattern matching. And if I say frequent, then that means above certain threshold. Disk resident graph, a graph is said to be disk resident if the graph is very huge, cannot be loaded into the memory, or cannot be processed by the algorithm all at once. So that means it should be worked on a part of in it is executed in part, and rest of the graph has been stored into the hard disk. So those type of graphs are called as disk resident graph. This topic is almost same as of the page fault in the operating system. In your COSS course, you might have learned about the page fault, paging. When the file is very big, it cannot be loaded into the memory. So only the recent part of the file which have been processed by the processor is loaded into the memory. Rest of the file is being stored into the hard disk. But when some content is required from the stored file, then this part of the file is being written back into the memory, and that part has to be fetched from the memory, and the work goes on. So the same concept is applicable with related to graph as well. When the graph is very huge, and even either huge or not required to load the whole graph into the memory. So for example, again we'll go back to this Google example, Google map example. My focus is only on this part of the graph, northern part of India. So that means this Himalayas and all the word graph need not to be loaded into the memory until unless I zoom out and specifically hover around my mouse onto that area. Okay, so if I zoom in, then rest of the graph is not required, so it need not to be loaded into the memory. So if I move into Indore, then the rest of the India will be of no use to me, so it is not visible to me. It is not loaded into the memory. Okay. There's a small word of caution. If you're using any algorithm that works on the edges or on the graph randomly, okay, like a random walk, okay, which path to even random walk also will be specific to the local area. So if you are at this node, you cannot disappear and reappear at this point of at this graph and at this part of the graph. Okay, so even for that also you will be roaming around in the neighborhood. So from Indore you cannot disappear and reappear in the Kanyakumari. You'll have to reach out to Kanyakumari first, and then you can move ahead from the Kanyakumari. So, but if there's any algorithm which is accessing the part of a graph randomly, then it is not advisable to use it on a disk resident graph. The reason being is the page fault will be high. Okay? So the algorithm using the random edges or nodes are not suitable for this certain graph because of high page fault. Because every time a new part of a graph will be required, and it has to be fetched, and the rest of the graph has to be stored by connected component. So if there are multiple part of a graph, all those will be called as component of a graph. Okay, so disconnected component and connect. So in that case, largest connected component means if a graph contains multiple part in terms of density, so whoever has the highest density will be called as LCC, largest connected component. Okay, there's a word which we call it as lowest common ancestors. So lowest common ancestors is being used for text mining. Okay, or we can say finding out the distance between two words in a graph. So suppose if I do have a text, okay, and text are being hyperlinked. Okay, one particular text have been, or those can be the web pages. Okay, so one web page is referring to another web page or something like this. Now, if that web page is of XML, so that XML, as you already know, that the XML data set is in the form of a tree. Default tree structure. Okay, so tree structure means something like this. So if I need to find a common thing, so suppose, for example, if this is one keyword, this is another keyword, how close they are. So that depends upon their common ancestors. If they have their common ancestors, so whoever has, so all the those two keywords, this one and this one, these are the keywords. So they all belong, their common ancestor, first common ancestor is this one. Okay, so this can be used to identify how close two keywords are. I'll show you an example where it is being useful. Okay, let me. ठीक है, चलो. Let me search for this text. Scholar.google. ये क्यों आ गया? Now suppose if I am searching for some text. Okay. So I was searching for computer and web data, the number of nodes in the underlying graph may be massive as well as so the edges, whatever this statement is. Now, so this is the web page. Now you observe one thing, the words which have been highlighted in bold are the words which are mapping into that web page. Okay, and they are close together. So dot 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 means they are in a different paragraph, but they still are close together. So similarly, these all are the web pages in which those keywords are mapping, and dot 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 means in a different paragraph. So that means the ranking of this web page is higher because all the keywords were more close to each other as comparison to this web page. Okay, so even this is used for a ranking purpose. Even the distance between those keywords is being used. So to identify the text mining name, semantic analysis name. I'm missing the word. Text in your ACI course. Give me some words regarding that is text mining, text semantic analysis name. I'm missing that word. That is something related to text. Means somehow we are trying to find out the relation between those keywords. If they are close together, means they are they are more relevant in the sense of in the terms of meaning. So the meaning of this sentence, whatever I was searching for, is more appropriate in this web page as comparison to other ones. Semantic missing it, but somehow it is there. So for them, what is the word which is being used is lowest common ancestor. So I'll have to come up with those lowest common ancestors and their combinations so that I can rank them. Clear? ठीक है. Somehow Aditya, that's okay. But I have not, matlab, I have included that splitting of edge just in a flow. I've not even properly thought of what should be the process. Okay. Now let's move back to the, so this was related to graph. Now move back to the codes. So now what all graph algorithm that we will be working will be classified broadly into two different classes, two different type of cases. One is single large graph. So for example, web graph, social media graph, and all those, in which we have a very large graph having millions of edges and millions of nodes and billions of edges. The number of nodes, number of edges in a graph will be comparatively higher than the number of nodes in a graph. So that will be one type of a graph that we will be working on, single large graph. Okay, even the computer network graph and all will be a single large graph. The another type of graphs that we will be working on will be the multiple graphs. But here again, multiple graphs means small graphs, but appearing a larger number of times. So a single large graph or small graphs appearing very frequently, not very frequently. We can say single large graph and large number of small graphs. Okay. So in another way, large number of small graphs. Where this type of graphs will appear in the chemical data and in the biological data. Okay, so these are the two areas in which we will be getting, or we will be working on multiple graphs. If I am working in the IT or the social media or the network and all, then we will be working on a single large graph. Okay, so these, and there's one more thing. The algorithms which works on this type of graph might not work in an exactly the same algorithm will not work or might not work for the multiple graphs. If we'll have to implement the same algorithm or similar type of algorithm on a different type of a graph, we'll have to make some changes into the graph. Okay, so here one nut will not be fit for the another bolt. Okay, so the nut bolt combination is there between the type of graph and type of algorithms. So I think we have discussed or not. I think this was the first thing that we have discussed. Lexical semantics. That's correct. Lexical semantics. Okay, in which you are trying to figure out the sequence of the word as well as with respect to the meaning, how they are connected to each other. Had I explained this diagram? I'm not remembering it. If I do have, then I can skip it. If not, then I'll have to devote around 5 to 10 minutes on this slide. Please confirm. This slide, various type of graph data. This is revisited. Okay, fine. So just for the sake of completeness, so these will be so single large graph, this one, single large graph, this one, single large graph, this one, multiple graphs, these, large number of small graphs. So what the various type of graph data, chemical data, they often represent as a graph in which the nodes correspond to the atom and links correspond to the bonds between those atoms. Okay, So the individual graphs are quite small, though there are significant repetitions among the different nodes. And the moment repetition with a different orientation. So this leads to the isomorphism challenge in the application such as graph matching or not. Okay, even for the area for pattern matching, frequent pattern. In the biological data, how it has been converted into a graph, we have different proteins of amino acids, ATGC in DNA, deoxyribonucleic acid, and AUGC in RNA. Okay, DNA is for multicellular organism and RNA is for the unicellular organisms. So all the viruses have their RNA. Okay, so AUGC, the thymine is replaced by the uracil. Even from those amino acids or those genes sequence, there is a different property of dominance and recessive. Sometimes same genes behave as a dominance genes and show its effect, and sometimes the same gene may behave as a recessive and does not show its effect. Two dominance, when there are two recessive genes clubbed together, they can show their dominance effect. Okay, I think if you do remember the George Mendel's P experiment in your high school or in, I think, in your 12th, in your biology. Okay, so that's again an area. So a single biological network would easily contain thousands of nodes. The size of overall database is also very large enough for underlying graph and that to be disk resident. So this is the area where the disk resident graph will be there. Computer network and the web data. So computer network and web data. So number of nodes are connected together by their hyperlinks. Okay. So here the problem can be either the massive domain issues. So it will be hard for available storage space. So either we need to summarize it and work with the condensed representation of a graph data such as Google Maps. The edges may also arrive in the form of a data streams. Okay, so if I'm dealing with the data stream, the new challenge will arise. It may not be possible to store the incoming edges for the future analysis. So in that case, therefore, the summarization techniques and the stream summaries may be leveraged for the future processing of those underlying graph. Even that's again we can say problem related to a huge domain of the graph. XML type of, this is the another type of graph data. But whenever we are dealing with those web graph, it will be XML data, and XML data is by default a labeled tree. Okay, so XML data is in the natural form of labeled graph data, and that too in the form of a tree. In addition to attribute value combination, the associated with the nodes make the problem much trickier since it doesn't. Fine. How much time do I have? Do I have time? 33, hardly 5-7 minutes. Okay. What you need to explain? Achha, that type of graph. Okay, fine. So just a quick summary. A different kind of graph that we will be working on. So the type of graph can be the social graphs in which the users as well as their interactions. So we have devoted around 15-20 minutes on this slide only in the first Cortex session. So if you're missing it, then I request you to go through the recording of the previous session. We have devoted enough time on various kind of graph and how they are generated and how even one social media graph, so one graph of Facebook can be different from the another graph of Facebook. Okay, so the user interaction graph of Facebook can be different from the video sharing graph. Okay, same for the WhatsApp. So text messages communication as well as audio message communication, as well as the text messages as well as GIF sharing and all. Okay, so I had hardly 7 minutes, so I'll have to finish this slide. Okay, so I request you please go through those first session PPTs. If you face any problem, definitely I will explain you in the next session. As of now, I'll have to finish this module. Real-time scenarios with the graph learning. It is assumed that the underlying graphs are massive and cannot be held in the main memory. Fine. The second is, in many cases, the problem of graph management and learning has been studied from the perspective of structured as well as XML data. So we have assumed that, or we for many of those activities, we have made our task easy by assuming that the graph that we are working will be structured or in the form of an XML. If XML, then tree structure. If my problem of if my data is unstructured or semi-structured, then it will lead to a problem and somehow I'll have to fix it. But for many of those, researchers have assumed that the data that they will work on will be structured or the XML data. Many of the graph algorithms are sensitive to the application scenarios in which they have been encountered. Okay, as I've already explained, if you change a problem, if you change the graph, the same algorithm cannot be implemented on the same type of graph. So for example, if some algorithm works well on a social media network on a single large graph, that will not be applicable for a multiple graphs. Not necessarily. We'll have to make certain changes into the algorithm as well as in the methodology to use the same concept or to use the same idea on a different kind of a graph. So you change the scenario, you will you'll have to change the algorithm, or you'll have to change the data. Different application results in different kind of graph, and corresponding challenges are also quite different. Okay, so that means social media algorithm which in influencing node on social media cannot be directly used in influencing researchers. Okay, so let me introduce this course at last after 3.5 or 4 hours of continuously speaking. Now let us formally introduce the course, which is GNN. So if I do have an image data, I can use convolution network. If I have a sequential data, I can use recurrent network, neural network. If I have a tracks data, I can use those transformers. But what if I have a graph data? Then in that case, I'll have to use all the mix up of CNN and RNN and all those transformers or all those encoders, and I'll have to modify them for our own need. And we put all those together in one topic. We call it as GNN, Graph Neural Network. So there are many real world problems that are typically they are structured in the form of a graph. So for example, social network. Social network, if you try to visualize it in a different way other than the graph, it will be difficult for you because their natural structure or their natural visualization is based on the graph only. Molecular structure in the basis of the chemical data and biological data. There are electrons, protons, neutrons, whatever it be. There are genes, there are chemicals, compound, non-metallic compound, non-metallic, whatever it be. They are in the form of their points and their interconnection and their bonds. So that also is in the form of a graphical structure. Recommendation system can be by default a graph structure. What is in an easy way? Prediction of new edge. Easy way of stating the recommendation system. How can I say? I have something. If I recommend him means I should point out something to him. I should share him with something to him only. So that means I'm predicting whether there should be a new connectivity from the existing one to the new point or a new person. So that by default is a graph structure. Fraud detection. Okay, so anything from the whole graph, if we have a very high connectivity, we can say inflow of those messages, or outflow of those messages, inflow of something, in inflow of money. So that means something fishy is going on. Okay, so if somehow we can convert them into a graph, it is easy for us to visualize. And drug discovery. Nowadays, it have been GNN or graph structure have been widely used for the drug discovery and the cancer predictions. Okay, so drug discovery or the disease prediction. Okay, so because for for identifying a new drug, we in a traditional way, we'll have to generate a new chemical and then experiment it on those rats and rabbits. Humans were not allowed. Okay, somehow we'll have to perform those, and then we'll have to observe the behavior of those rats and rabbits into the lab, and then we can say something about the drug. It was costly and time consuming. If somehow we can convert them in the form of a simulations, okay, bonding and their interconnection, if we can simulate the chemical reactions into a computer program visualization one, it will be easy for us to perform the experimentation. We can just drag the buttons and reduce the composition of a particular salt, okay, or in a mixture. We can easily do that, and it is easy for us to, okay, so drag those buttons and perform the experiment, reduce the concentration, and then execute the algorithm again, execute the simulation again. We can easily do that, and it's non-hazardous, although it will be consuming the electricity and the computer memory, but will not be doing it on the rats, waiting for their output. So that's again an area. So huge demand in industry for people with GNN expertise nowadays. Wherever you have, so ultimately, wherever you want some activity to be to be done based on the prediction. Okay, either this is a node prediction or an edge prediction or a graph prediction. The best method that you can use is the GNN, neural network. And the another beauty is why only neural network? Because network, a neural network, can be easily implemented using the graph structure. So that graph itself will behave like a neural network. You need not to identify the structure of the neurons and all those things. Graph, node, and their neighborhood will themselves behave as a neurons into the graph. Okay, so that's why GNN is widely being accepted or widely being used for all type of prediction activity, for all type of classification activity. And if we will be moving in the area, then obviously you will play a key role. Not me, I'll still be a teacher. I'll still be teaching GNN to someone else, but once you have learned, you will be applying the knowledge gained by yourself, not through me, gained by yourself, but by reading those books and preparing for the exams, and you'll be implementing it into your own day-to-day life. Tools: GraphDB, Neo4j, NetworkX, PyTorch, Tensor, and all those. So you can use any of those tools, okay, or all of those tools if you can generate the familiarity for your own work. So there are n number of tools available for the whole graph. So by this, I finish, and I'm 4 minutes late, but somehow I'm able to finish this first module. Okay. So I'm done. I'm ready to answer the question. Now, the only thing left is, what is the meaning of complete in the NP complete? I've not even thought of why it is complete. I'll ask, I'll discuss this with my friend, and then we'll come up in the next contact session. So Bhupendra, was it you who had asked this question?
Yes, sir.
Okay, okay. So I've not even, I cannot even guess what should be the proper statement that I should make. So I should not make any false statement. It's better I will take this query to the next session. Clear?
Yeah, thank you.
Anything to be discussed on record? Or should I stop the recording? Okay.